Hey guys, it's Mr. Wolfe here, and we're going to be going over target one. And so here's your guys' target sheet. I kind of blew up mine into two sections just to make it a little bit easier for you guys to see. But if we look at target one, there's a lot to it. I can analyze situations where the net force is zero and determine individual forces acting on an object and can draw and calculate the resultant of two or more vector quantities. All right, it sounds like a mouthful, but it's really not too bad. And to even make it not too bad, uh, the target sheet we're going to be working on is only going to be, and I want you guys to underline this, is can draw and calculate the resultant of two or more vector quantities. That's it. All right, so what is a vector? Well, in order to establish what a vector is, we also need to know what a scalar is, right? So in physics, quantities can be scalar or they can be vector. And so a scalar quantity is going to have magnitude. And when I say it has magnitude, that just means that, let's say we're talking about time. Time is a scalar quantity. You could say we have 2 seconds, or maybe volume is also a scalar quantity, and we have 25 centimeters cubed, all right? So really just that number is talking about the magnitude right there. All right, so let's go over to a vector quantity. A vector quantity is also going to have magnitude. So an example of a vector quantity is going to be a force. All right, and we could say that we have a force of 5 newtons. Another vector quantity, and we're going to learn about this very soon, is going to be called acceleration. And let's say we have 2 meters per second for acceleration. Okay, so what's the difference between scalar and vector? Right now they look the same. Well, the difference is a vector quantity, and this is how I like to go about remembering them, is I like to kind of, like the V in vector will make an arrow. A vector quantity is going to include magnitude and this is a very important and, direction. While a scalar quantity is not going to include direction. So I'm going to write direction, and I'm just going to cross that out. So no direction for a scalar quantity. We're only dealing with magnitude. And that makes sense, right? Like time really doesn't have a direction. Volume, you can't have a direction with a volume. Another example of a scalar quantity could be area. No, we really can't have direction with an area. Right? But a vector quantity is going to include direction. And we've been able to represent the magnitude in a vector quantity with the number, right? The magnitude is 5 newtons, or magnitude is 2 meters per second per second. But how are we going to represent direction? Well, in physics, we're going to be using the positive and negative sign. All right, so if I write here positive 5 newtons, what I'm saying is that this object is going to, let's say, the right. Right? And if I have an acceleration of -2 meters per second, I'm going to the left. Right? And this is a very, very important thing to keep in mind, especially coming from a lot of your math classes where -2 seems like it's less than 5. So for example, let's say I have 2 meters per second. And in this case, I just put a positive next to it. All right? These numbers are exactly the same in terms of their magnitude. The only difference is this one, it has an acceleration going in the positive direction, or we can maybe say to the right in this instance. All right, so we're not always going to the left or right. So just in general, when we use positive for a vector quantity, it could mean to the right. But we could also say that it might be moving upwards. We'll use positive signs for upwards, and then maybe like north and east. Right? We'll use a negative when we're talking about something going to the left. All right, downwards and south, or maybe west. Right? And you could always write these things out too, but in general, it's just it's a lot easier to use a positive or negative when talking about direction, especially when it comes to working out problems. All right, so that's the difference between scalars and vectors. And so, what's this big thing with vectors? Well, it's very, very important to incorporate this direction, especially when solving complex physics problems. So here's an example. This is just going to be at the bottom of your physics sheet. And here we have an example of, this large guy with a lot of strength playing tug of war with these three little dudes right here. All right, and what the question is asking is how will the rope move? And so our rope is our object of interest right here. And so in physics, what we do is physicists are not great artists. No matter how complex the object is, you could just draw it as a box. So our box is going to be our rope in this instance. And in order to solve this problem, and by the way, we're going to be solving this using vectors because we have vector quantities here, let's first identify our forces. And we're going to draw it out. Always just draw out your problem first in general when doing really any type of physics problem. So 500 newtons, and I'm going to draw this by drawing an arrow, all right, for 500 newtons. I'm also going to just write down 500 newtons because it doesn't hurt either, all right? And then, so there's a force being applied to the right, and that's shown by that positive right there, and so we drew that vector. All right, so let's look to the left as we have these guys pulling with 100 newtons. Well, what direction? Keep in mind, they could be pushing this rope too, but our number right here, negative, tells us that they are pushing it to the left, all right, with negative 100 newtons. And you're going to notice that I'm drawing these arrows much smaller. So when we draw vectors, vector arrows, we want it to represent the magnitude of that number. So, and I'm also just going to write 100 newtons because it always helps to do it. All right, so now we've set up our problem. There's two ways we could go about solving this, and you guys are going to need to be able to master both. We could solve this mathematically or visually. And sometimes you're going to be doing both with one problem. All right, so how are we going to solve this mathematically? Well, let's look back to our question. How will the rope move? And in parentheses, specifically, we want to know the net force and the direction of the rope. All right, so this right here, this sigma F is our net force. And we haven't talked about it yet. But essentially what we want to do is we want to look at all the forces acting on our object, our rope, add them all together, and what we get is going to be our net force. And I'm going to explain this a little bit more in our next video as well. So mathematically, my net force is just equal to adding up all the forces that are acting on the object. All right. So I'm just going to kind of draw dot, dot, dot. All right, our net force then, and this is just in general, I like to start with my positives first, is we have we have a force of positive 500 newtons, so 500 newtons, all right, plus, and then what's my other force? Negative 100 newtons plus my other force, so I have three negative 100 forces acting on my object. Now, you can write this like this, just the net force is equal to, you start with your forces acting in the positive direction and then just do minus 100. The reason why I like drawing it like this is because it helps hit home the idea that the net force is the sum. You just add up all the forces together, all right? And then what we could do is we could simplify this equation to, 500 minus 300. What we're going to get is a net force to be 200. 200 what? It's very important we include the units. 200 newtons. All right. And so we're looking for the net force though. And if I go back to the sheet right here, force is a vector quantity. So we want to include that direction. All right. And so my answer, my mathematical answer didn't include, a negative number. It's positive, but we want to highlight that. So I want to show this positive right here, and that highlights, that emphasizes the idea that this, first of all, this is a vector quantity, and it shows us that the net force acting on this rope, the rope in general is going to be moving to the right with a force of 200 newtons. All right, let's solve this visually now. All right, and this is going to be called the tip to tail method. And I'm going to be kind of going through this in steps when you guys solve this, and when I'll be solving these on the board with you guys. We'll do it all one step, but for the purpose of your notes, I'm going to, draw multiple steps. So what we're going to want to do is we're going to want to have a starting point. Right? And from that starting point, I'm going to just, same thing with I did mathematically, start with my forces going to the right. Right? And so I have a force of 500 newtons going to the right. And again, you don't always have to be so repetitive with drawing this, but it helps for a step-by-step process when looking at your notes. All right, now I don't have any other forces going to the right, so I'm going to be looking at my forces going to the left, my vectors going to the left. And since it's the tip to tail method, I'm going to start at the tip of this vector, and I'm going to start the tail of my next one, and my next vector happens to be going to the left. All right. And then I'm going to do the same thing right here. I have another force of 100 newtons. I'm going to start at the tip of my last arrow and start the tail of my next, right? And since I have three 100 vectors, here's something that might look like this. All right, so sometimes when you solve this, you guys could use a ruler. You know, keep in mind my arrows don't look perfect. Right now, we're just kind of eyeballing it. But sometimes you will use a ruler just to get more of a accurate representation. All right. So what do we do then? Like, how do we determine the net force or how this object is going to move? Well, I'm going to redraw kind of everything again. All right. So we have our start, and we also are now going to draw our finish. We're done drawing our arrows. Now we're going to work on drawing our resultant. Right? And our resultant is just essentially the net force right here. We're going to start at the start and draw an arrow. I'm going to draw this one just a little bit bigger, just to highlight that this is the resultant, and draw it to where we finish. Sometimes your finish might be over here, and that means our object is going to be experiencing a net force going to the left. But this is agreeing with our mathematical problem, or our mathematical answer is that we have a net force going to the right, and that's what this tip to tail method shows us here. Now these arrows not only show us direction, but they're going to show us magnitude. Now granted, we were eyeballing this, but this arrow right here looks like it's about 2 of these negative 100 arrows. So the magnitude seems right, that this could be about 200 newtons going to the right. So these two problems, even though we solved them in different ways and you might be using them for different reasons, both agree with each other. And so again, this arrow right here is going to be called our resultant. Essentially the result of all these vectors being added up together. All right? And essentially what this resultant is, in this case, is the resultant represents our net force. All right, so that wraps up scalars and vectors. Remember, scalar quantities only have magnitude, and vector quantities have magnitude and direction. And we're going to represent that direction using a positive or negative.